Hello, everyone. My name is Scott Grizzard from the University of South Florida. And this is Calculus. This is Lecture 2B on the 3rd of September, 2020. And tonight we're going to be talking about how to write proofs. So the first four lectures, especially the last three lectures, 1B, the first three lectures, especially the last two, that would be 1B and 2A, have really been about definitions, concepts, strong concepts such as the definition of the function, the definition of the limit of a sequence, and the definition of the limit of a function. Now, tonight we're going to talk about something that is kind of the difference between the math you've taken before and now the math you're taking now. So in calculus now, we're going to suddenly start being worried about proof. Now, this has, unfortunately, there's damage done in high school about proofs. When you do them using Euclid, you do the geometric proofs. So when you did geometry, there's this like horrible thing that happened where you got totally turned off by a proof, where you had to use this, like these tables and say, oh, this is true by proposition this, and this is, we're not doing that. Okay. We're doing more. It's not that they're, I want to say not less formal, but less formalistic proofs. So what we're doing in this class, and we'll show you that, is we want to make mathematical arguments. And it's really about writing. So when you stop thinking about proof so much as think about writing, it's really more of an English thing. I mean, yes, there's math, there's logical rigor involved, and that's important. But there's also something a little bit more, there's also something craftsman and artistic almost, even, very artistic, and much more English type thing, because we want to be able to communicate. So it's not really about the proof so much as the writing of it. We want to take a complex argument, we want to break it down, and we want to summarize it, and then be able to explain it to someone else. Again, don't panic. The big thing about it is that you've got all this stuff about high school geometry. And we want to de-scare this word proof, okay? Now, on the test, you may see the word prove. You may see the word show or demonstrate, because we don't want to use the scary word proof. But they're all the same thing. So let's just talk about what a proof is and how to write one. Last time we talked about the definitional limit, and we did this theorem, 2 cops and a drunk. What we want to do tonight, and we want to prove a couple things using the definitions and using this theorem. And when we do these proofs, you'll see that the language is a little less formal, but it also has this kind of 5-paragraph structure. You need to write a kind of introduction. And I cannot say this enough. The key to proofs in this class is the introduction. Okay, so that's the big idea for today. Now, we're going to have other ideas that are very important, like how to apply a theorem and how to meet a definition. And those are very important things. But the big idea is that if you write an introduction, your proofs will be you'll clobber the thing when you do it. Now, as a reminder, there is chat in 2 places. So there is chat in Discord that is private only to the class, and there is chat over there in Twitch, which bear in mind that if you do it, it's public and anyone can see your messages. So are there any questions before we begin? Okay. I think there's probably 3 people watching, and one of them is me, and one of them is is the TA. So, welcome, other person. that are watching it live. Obviously, people are going to be watching this on YouTube later. But it's just funny to me. Okay. So, again, what we want to talk about is how to write proofs. And we don't want to get bogged down in this high school geometry type thing. Okay. So let's start talking about, let's just do a proof first. What we want to show, so write this as a theorem. Right now we have a bunch of limit problems, okay? So we've been solving limits by factoring and doing all of these limit laws, okay? And we had a set of these limit laws. And they included things like a sum law, right? We had the sum law, a constant multiple law, a product law, and a bunch of other little things. Okay? So let's just review what we had. We had some limit laws. All right, so we had the sum law. And then we had a constant multiple law. What else do we have? We had a product law. And that was I'm writing a little bit too. I'm cutting off Ramsey here, which is rather rude. Let's get him over there. The quotient law. I don't know if I can do this. Yeah, that's better. And I had the limit of the identity and the limit of the constant. So let's do those real fast. This is the limit of the identity. And here's the limit of the constant. Okay, so now what we want to do is we want to talk about, and the natural power law. I always forget that one. There's also a root law, but I don't really need it right now. I'll use it later, but I'm not going to write it right now. Oops. This is the power law. So I had all these laws. with their abbreviations. And if you go to the notes online, or if you had the activity packet, you had them before. And I want to do, so if what I want to do is I want to prove something like, so I want to say something like the example, the limit as x goes to 4 of x plus 1 equals, and then I say, okay, well, I'm going to take the sum law. I'm going to break it up. And then, well, this one's the limit of the constant. And then this right here is the limit of the identity. And it's rather tedious, right? I mean, that's a short little thing, and I used a lot of space to write it. But we have a theorem here. And wouldn't it be nice if I could just like sub things in? Right? I mean, it's clear that if I took 4 here and stuck it in there, I would wind up with 5. Okay? But how do I know I can do that? Okay? Well, this right here is an example of something called a polynomial. So let's define what that is. And we'll call it P. So let P be some function from R to R. All right. Recall that this just means domain and then target. P is a polynomial if there exists a finite list of real numbers called coefficients so that f of x, for all x and r, f of x equals finite list of real numbers. I should say what the finite list of real numbers is. A0 dot 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 an coefficients. So the f of x equals a0 plus a1 x to the first plus a2 x squared plus dot 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 plus an x to the n. Okay, so that's a very complicated way, because you've got this thing of saying it looks something like x plus 1, x cubed plus 4. These are all examples of polynomials. So, examples. G of x. Oh, this should have been a P. I'm sorry. So, examples. G of x equals x squared is a polynomial. Right? A0 equals 0. A1 equals 0. A2 equals 1. F of x equals 5x to the x cubed plus 3x minus 2. In this case, a0 equals negative 2, a1 equals 3, a2 equals 0, a3 equals 5. How do we feel about that definition 1 to 5? Okay. So these are all polynomials. Okay. Another example. C of x equals 5. And that's just the constant function 5. And in this case, a0 equals 5, and that's it. Right? So I can't have a constant. I can even have the 0 function. a0 equals 0. Okay? All right. These are just polynomials. Now, I'm going to write a theorem. And it's a theorem that you're going to love. Okay? The theorem is simple. The theorem says the following. If f is a polynomial, then for any a in the x space, the limit as x goes to a of f of x equals f of a. Okay? That's all it says. So what it says is if I wanted to know, example, the limit as x goes to 1 of 5x cubed plus 3x minus 2. All I do is I take the 1 and I just plug it in. That's kind of a nice little thing to have around, right? I don't have to do anything. I don't have to evaluate this. I don't have to break it up into all of its things. All I do is I write ds over the top. I directly sub in, and as long as it's a polynomial, I can do that. How do we feel about that? 1 to 5. I just take my number and I throw it in, and now I have everything that I need to know. I don't have to sit there and break everything up using these laws. Right? I don't have to sit here and write sum law and then power law and then constant multiple law and then limit of identity and then limit of a constant. I don't have to do that. I just take my number and I toss it in. All right. It's kind of nice. Okay. Well, now we need to prove it. By the way, this is called the direct substitution property. Okay. And it's in your book. I'm not doing something strange. It's actually in your book. Speaking of which, the definition of the limit's in your book too. So, you know, people are like, oh, Scott's going nutty. Not really. Okay, a little bit, but, not really. It is in your book. All right. Let's prove this. Proof. That word. Scary word. The scary proof word. Let's prove it. All right, well, what is it I want to do? What is it I want to say? I want to say that the limit of this equals that. Okay? So what I really want to say is that the limit as x goes to a0 x to the 0 plus a1x plus a2x squared plus dot 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 plus an x to the n equals a0 plus a1 times, I used an a there, I'm sorry. Let's use something else here. That's going to be confusing. Let's do b. a1b plus a2b squared plus dot 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 plus anb to the n. That's what I want to show. Now, how am I going to do it? Use the limit laws to break it up. And so notice here that I'm not doing it for some particular polynomial, right? I'm not proving it for 5x cubed plus 3x minus 2. I'm doing it in general. This right here is the definition of a polynomial, right? A polynomial is a function with these coefficients a0 to an so that this is true. And what I'm trying to say is that I can just take b and plug it in for x. Okay. So how do we feel about what we're trying to do, 1 to 5? Okay. Well, let's do it. Okay, I'm going to call this P of, excuse me. Okay. So let's do this. P of the limit as x goes to b of a0 plus a1x plus a2x squared plus dot 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 plus anx to the n equals, by the sum law, the limit as x goes to b of a0 plus the limit as x goes to b of a1x plus the limit as x goes to b of a2x squared plus dot 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 plus the limit as x goes to b of anx to the n. So I just broke up this huge sum using the sum law. Okay. Well, let's do something about this. I can get rid of the constant right away. And I can also pull out these constant multiples, but I don't want to do both in the same step. So let me just do this. So what I'm going to do is I'm going to pull off the constant first. And I'm going to get, the limit of the constant. And I'm going to get a0 plus all this stuff again. This becomes a little baggage I just have to carry around. All right, so I've gotten rid of that first term. Now, what I'm going to do is I'm going to pull off the constants, the constant multiples. All right. Well, I could do this identity here, but let's just hold off on it. I've got a whole bunch of stuff here that I can get rid of. Right? I'm sorry. I've got this whole bunch of stuff here that's got powers on it. This one doesn't have a power. It has a power 1. But all of these have powers. Let's get rid of those. So all I did was apply this rule right here a bunch of times. I pulled the n, those positive integers, out of the limit sign. All I did. Okay. Well, now this is off by itself. It's fine. It's just hanging out. This right here is the limit of the identity. This right here is the limit of the identity. This right here is the limit of the identity. So each one of these can be evaluated now. And that's it. I've proven it. How do we feel about that proof? That's all it was. This is a long chain of equalities, right? I had the definition of what a polynomial was, and I wanted to show that I could just take B and sub it in and get the exact same answer. 1 to 5, how do we feel about that one? Okay. All right. So it's not bad, right? It wasn't horrible. It's just a little, Now, how did I write it? Do you see what I did up here when I said, I said what I wanted to show, and then I said how I was going to do it. I'm just going to use the limit laws and find the limit. Okay? And that's what I did. And then I had this little tagline at the bottom. All right? This right here is the introduction. And it is the key to writing a decent proof in this class. Okay? It's also the key to memorizing your proofs. I say what I want to do. This says that I understood what the problem was. This says what I was planning on doing about it. And then this is just kind of I did what I said I was going to do. That's just a tagline, a conclusion. This right here is the body. Now, people say, oh, but you just get graded on the body. No, you get graded on a dot more than that. Right? Now, if you had a perfect body, you'd get that sentence sounded horrible. You'd get the, full points. But it's hard to get the perfect body without stretching first, without writing this introduction. Okay? And if you make a mistake here, this can save you. And that's why these introductions are so important. So this is not a step to skip. Now, if you pull up if you go up on WebAssign, on Canvas, okay, and you slide on down here to the file section. You come down here to where it says rubric. There's a meta rubric for proofs right here. This is kind of what happens is we take this and then we have a particular problem. We have this, and using this, we create a rubric for the proof in question. Right? So like for instance, if we asked you to prove this problem we just did. Now, look at the top of this thing. Student understands the problem. Is there a way for me to open this in a real, realish thing? Okay. So this says here, if you can read this, student understands the problem and demonstrates that. Student had a strategy. Overall strategy laid out, easy to follow, correctly solve the problem. Mathematical symbols used correctly, fluency. The details. How neat it is. All right. Now, let's look at my proof and grade it using this system. Now, if all I was looking at was the body, yeah, the student understood what he did. I mean, it was a perfect proof. But what if I had made a mistake? What if I had accidentally left one of these 2's in, or forgotten to pull this A2 out in some way, or accidentally did one of these things first? It's now very muddy whether or not I understood the problem. But look at my introduction. I said what I wanted to do. This student understood that what they needed to do was show that it worked for a generic polynomial based on the definition. So, before they've even read the body of my proof, I've demonstrated that I understood the problem and I've locked up 3 points. Strategy. My overall strategy is racked up. I'm going to use the limit laws. I've locked up 4 points. So, of the 15.5 here, I've now locked up 7 before my body has even begun. How do we feel about that, 1 to 5? Let's do a slightly more difficult one. So we had this theorem last time called 2 cops and a drunk. Let's state that theorem again. We're not going to prove it. Proving this one requires the definition of the limit, and it's rather tedious, and it doesn't add anything. But let's prove stuff with it. We had this theorem, 2 cops and a drunk, right? Let top, bot, and f be real functions. A in the, or near, EX space actually. Come on. Let's just say X space here. All right. Now, if we had 2 conditions, if for all x near A, top of x is greater than or equal to f of x, greater than or equal to bot of x, and if the limit as x goes to A of top of x equals the limit as x goes to A of bot of x equals L, then the limit as x goes to A f of x exists, and the limit as x goes to A of f of x equals L. Come on. And yes, I did have to draw the quick little drawing to remember it. So how do we feel about this theorem, the statement of this theorem? 1 to 5. Okay. All right. There we go. Okay. So let's take it out for a spin. Let's prove something. Let's prove we want to show, so our theorem is that the limit as x goes to 0 of sine of x equals 0. Okay? That's what we want to show. I'm going to write an introduction. Want to show the limit as x goes to 0 from the right, sine of x equals 0, and the limit as x goes to 0 from the left of sine of x equals 0. Now, I'm going to leave a little space here for a strategy. We'll do that last. Let's start with this right side. Now, I want to prove a limit, and that means something in particular. I need to show that the limit from the right and the limit from the left are both 0. Okay, that's what I need to show. So we'll leave a little space here. Now, let's make a little circled kind of diagram here. Oops. Excuse me. Well, what about this little diagram? Let's see. This right here is x. Okay? It is the length along the unit circle from here to here. This length here is 1, by the way. And this blue length here is x. Now, the sine of x is its northiness. The cosine of x is this thing. And this thing right here is called the chord of x. It's the length from here to here. So the first thing I'm going to do is I'm going to let x I want to show this part first. So I'm going to say, okay, let x I want to show as it goes to 0 plus. So I want to show that it's from 0 to, we'll do pi over 4. It doesn't really matter. Anything in pi over 2 would work. But let's just put x here. Because remember, what I want to show is that as x gets closer and closer to 0, this height goes to 0. So I want to show that this goes to 0 as x goes to 0. Okay. Well, notice the sine of x is less than the length of this chord. And that this chord is less than the length of the arc around the chord. So I have So sine is always trapped above by x and always trapped below by 0. Okay. Well, the limit as x goes to 0 from the right of x equals 0. And the limit as x goes to 0 of 0 from the right is, let me think here, 0. Right? Thus, which is right near A. So how do we feel about that 1 to 5? I know I'm off a little bit. How do we feel about that? All I did was for anything right near A, I trapped this. I got a trapped at a sine of x between 0, which is always lower, and the length of this arc, which is always greater. Okay. Well, I showed one side. I still need to show the other. So if x is negative, I multiply everything through by -1, and I'm back to this side. Oh, but I need to flip the signs. Sorry about that. If that is not convincing, how about this? Okay. So I can, if I want, if you don't find this argument convincing that I could just multiply through by -1, find this argument convincing. So x is going to be the smallest thing. Right? Now, x is more negative than CRD of x, which is more negative than sine of x, which is more negative than 0. So now top of x equals 0, bot of x equals x, because remember, x is negative, right? And by 2 cops, and okay. And now I need a tagline. What would be my tagline here? I know this picture is horrible. Sorry about that. My tagline would be the limit from the left. So the limit from the left is the same as the limit from the right. and the limit as x goes to 0 of sine of x equals 0. How do we feel about that 1 to 5? Okay. Negative side's a little bit harder. Right? You have to remember these inequalities, and that's unpleasant. Okay, now how do I write an introduction for this? What was my strategy? What did I do? Well, what I did for arcs near 0 on both sides, apply to cops using x and 0 as the patrol officers. All right. And that's it, right? Now, I may need to memorize the diagram, but what do I memorize for a test? If Scott said that proving that the limit as x goes to 0 of sine of x was going to be on the test, or could be on the test, what do I memorize? Do I memorize all these details line by line? No. The only thing I memorize is my introduction and my diagram. How do you feel about that 1 to 5? That if I understand two cops, I can use this and that diagram to reconstruct the whole argument. How do you feel about that? This idea that I can reconstruct the entire argument from a memorized introduction. Okay. All right. The theorem that the limit as x goes to 0 cosine of x equals 1 is on the notes. I'm not going to repeat it because I want to do one last major theorem today. So as an exercise, I encourage you to read that proof and then try to create a diagram for you in an introduction. So this is the theorem, the limit as x goes to 0 of cosine of x equals 1 in notes. Okay. Let's do one major one. Let's see. This is called special limit 1. So the first thing I need to remember the area of a sector. So if you don't remember the area of a sector, this is what it is. Okay. If I have a quarter of a pizza, the area of my quarter pizza is 1/4 times pi r squared, where r is the radius of the pizza. I take portion percentage, let's do percentage of the circle and multiply by the area of the circle. If the angle or arc is given in radians, I do pi over, x over 2 pi r So everyone remember that there are 2 pi r radians if I go all the way around the circle. So if I want the percentage of the circle that I have, I take my x and I divide by 2 pi r. And that gives me the fraction of the circle. Times pi r squared. And something nice happens here. These pi's cancel. And that square goes away with that r. And so I wind up with x over 2 times r. So I wind up with xr over 2 for radians. 1 to 5, how do we feel about that? Just kind of this little sidebar. 1 to 5. Okay. I just take the percentage of the pizza. I just take the percentage of my pizza and I multiply it by the area of the whole pizza. And if you remember that, you can remember the arc of the circle. Right? I got a quarter of a pizza. Right? The area of the whole pizza was a certain number. So I multiply it by the quarter and I get the area of my quarter pizza. This is a very complicated way to say that. So I do x over 2, right? So if I have 2 pi r of the circumference and I've got pi over 2, right? If I've got pi over 2 of the 2 pi r, I've got a quarter of the circle. That's just this little sidebar I'm going to need here. All right, what I want to show, this is a big theorem for us. We need this in order to prove stuff. We're going to need this later in order to prove the derivative of sine. This is called special limit 1. Okay. It says that the limit as x goes to 0 of the function sine of x over x equals 1. I'm going to put some stars by that. Maybe some highlighting. All right. Proof. I'm going to leave a little space for stuff. All right. And what I'm going to do is I'm going to pull out one of my little diagrams again. All right, and here's my diagram. Let's move the pizza sidebar up a little bit here. Let's get it out of the way. Okay. So I'm going to start with this diagram here. Let's make the diagram bigger. And let's put it right here, because I want my face right in front of it. All right. So this is a diagram. This is that same diagram I was talking about in the quiz last time, where the tangent, sure, it's sine over cosine. That's what it's equal to. But it's really the length of this line. And what I'm going to do here is something I'm going to do the same thing that I did last time from the left and from the right. But what I'm going to do is I'm going to compare these areas. I'm going to talk about this big triangle out here. And I'm going to compare that to this little triangle in here. And then I'm going to compare that to this big sector right here. So I've got three pieces here, okay? I've got three triangles. I have the triangle, I have two triangles and a sector. I have the sector swept out by x. Okay. I have the triangle formed by the tangent and the sine. And that's in purple. And then I have the smaller triangle. Sine and cosine. So how do we feel about this diagram? What exactly I'm looking at? 1 to 5. This pencil is really light. That doesn't really work, does it? Let's make this darker. All right, so those are the things I'm playing with. Okay. Now, if I'm looking at this diagram, I've kind of already given it away that it's big and thing, right? So let's do the things. The sector, the area of the sector, is x. Oh, and the radius here, by the way, is 1. This is the and radius. Sorry. So the big triangle is this one right here. Now, the area of the sector. The area of the sector was x over 2 times r. And since r is 1, that's x over 2. Now, the area of the small triangle. What's the area of a triangle? It's 1/2 times the base. The base here is sine. Is cosine. Times sine of x. And the large triangle this piece right here is actually a right triangle. There's the right angle. This is the hypotenuse. This right here is the tangent of x, and this right here is 1. So if I flip this on its side a little bit, I just kind of go, I wind up with a base times height of tan of x times 1. And then, of course, the 1/2. How do we feel about that? 1 to 5. Two-ish. Okay. So, pi over 2. Then I have the fact that 1/2 cosine of x sine of x is less than or equal to x over 2 is less than or equal to 1/2 tan of x. Now, what's the first thing that should go away? Just bye-bye. The 2's. Okay? Now, this right here is sine over cosine. It's equal to that. I mean, we can have that big philosophical discussion about what it is, but that's what it's equal to. Oops. Yeah, there's no way to get that without dragging tan of x, is there? I can probably do it now. Oop. Okay. All right, so let's ditch the 2 and let's rename this what we've got. So we've got cosine of x sine of x is less than or equal to x is less than or equal to sine of x over cosine of x. Now, is cosine in this neighborhood between 0 and pi over 2, is cosine ever 0? And the answer is no. Moreover, I mean, it is at pi over 2, but I'm not including pi over 2. Moreover, it's always positive. So what I can do is I can multiply through that what I want to do here? No. I want to divide through by sine. Yeah, that's better. So sine is always positive here. So what I'm going to do is I'm going to divide through by sine. I wind up with cosine of x is less than or equal to x is less than or equal to 1 over cosine of x. Now, if I take the reciprocal of this, oh, that's what I'm forgetting. Okay. Divide through by sine because I want x over sine of x. It's late. I'm sorry. 1 over cosine of x. There we go. That's fixed. Now, what I'm going to do is I'm going to take the reciprocal, and I wind up that the cosine of x is greater than or equal to sine of x over x, which is greater than or equal to 1 over cosine of x. Remember to flip signs. Okay. Well, where do I go from here? Well, now I've got something interesting. The limit. What is the limit as x goes to 0 of cosine of x? Moreover, the limit as x goes to 0 of 1 over cosine of x equals 1 over the limit as x goes to 0 of cosine of x equals, well, 1 over 1. And that equals 1 today. But it's a special. So, my two cops how do we feel about that? That proof, by the way, is in your book. There's a 1 to 5. How do we feel about that? I still have 11 people watching, so, it can't be that horrible. Or it is that horrible. And, okay, it is that horrible. I got 2s, 3s, 2s, 2s. Okay. All right. But that's the idea. Now, notice how I applied this theorem. I applied this theorem by chasing after this diagram because I needed to get the first condition here of two cops. I needed this to be true. Does everyone see that? I needed this thing to be true right here. And because I needed this thing to be true, that's why I drew my diagrams. And then I set it up for this. Now, this one's a little out of left field, this proof. But we could write an introduction for this. Let's talk about what needs to go into the introduction. I'll leave some blank space, so you to do. You write an introduction, and then you write the other side. Now, what needs to go into the introduction? Let's talk about that. Let's see. Did I put this? Yes, I did. Okay. So what I want to do, I want to write first, restate the problem in your own words. Two, describe the strategy. One thing that doesn't work on the online thing is that I can't suck you in and go, well, what is it? What is it? What is it? And then call on people randomly until I get an answer, right? Because that's what I do in classroom. I'd be like, well, you're not speaking up. Tell me what you think. I can't do that. Because you can log off. Draw any diagrams. And explain any intuition. and then state any rabbits you need. And we'll talk about rabbits later. Okay. We'll talk about rabbits in Module 2. All right. So, talk about this. So after test 1, we'll start having proofs with rabbits. And again, the big thing about a introduction is that's the thing I memorize. I memorize the introduction. Okay? And so I write it last. I write an introduction that works for me. And I write it to be tight, nice, concise. And have enough detail that I can reproduce the proof from it, but not so much detail that I get bogged down in memorizing details. I don't want to get bogged down memorizing details. I want to memorize the big picture. What did I have to do? I had to draw a diagram that made it so that I had to draw a diagram that got tangent on one side and cosine times sine on the other with x trapped in the middle. Then I had to divide through by sine, and the proof follows. And then apply 2 cops. And that wound up trapping everything between cosine and 1 over cosine, which both go to 1. All right. What does it say after draw any diagrams? Oh, and explain any intuition. So if there's intuition behind my proof, I want to have it here. And that's going to be big in the proofs. That's going to be big in the proofs like the product and chain rules, especially the chain rule. The chain rules has a lot of intuition in it. Okay. Are there any questions? All right. So today we kind of talked about writing proofs, kind of how to do it. Don't be panicked by them. They're not something to panic. The ones we'll be doing in this class, they'll be we're going to do problem set 3 is how to prove that that using these special limits, how to prove a particular limit that winds up being the derivative of sine. So we wind up proving that the derivative of sine is cosine. That one's really important. And then just this idea of what I do when I want to learn a proof is that I just write an introduction. And if you look at my notes for my math, you'll always see me writing little introductions by the side. You'll see WTS, want to show everywhere. All right. So that's it for today. Oh, I do have one announcement. Starting next week, people have been having trouble with quizzes. And remember, there's no quiz. Monday's Labor Day, right? Yeah. There's no quiz on Monday. There is a lecture in the evening, but that's because I'm recording it for Tuesday. On Monday evening. But there's going to be no more. Starting on Wednesday, I'm going to be broadcasting the quiz reviews in both Twitch and Blackboard Collaborate Ultra. Some people are having trouble seeing the board in Blackboard Collaborate Ultra. Twitch, does 1080p. So I'm going to start broadcasting just the quiz reviews in Twitch. And in Blackboard Collaborate Ultra, but the Monday, Wednesday class is still in Blackboard Collaborate Ultra. And I will make an announcement about that and everything. Also, because we don't have class on Labor Day, everyone has to, the required class is on Wednesday. So everyone has to show up on Wednesday. All right. That's it. Any questions? Okay, well, thank you for the 10 of you. There were 11 at one point that sticked with me tonight. The video, of course, will be uploaded to YouTube as soon as I'm done editing it, probably tomorrow. And I will see you guys later.